Hi, and welcome to my discussion of moving into an understanding. We're not going to quite talk about all of the properties right now of ionics, but laying the groundwork for understanding the ionic compound properties. And I call this level 2. This to me means this video is probably more appropriate for AP, IB, or college chemistry than it might be for 10th grade chemistry. But man, if you have got some good 10th grade chemistry students, go for it. Okay, so we're going to look again at Coulomb's law. Coulomb's law, I didn't used to use it a lot in my teaching, and I use it more and more and more. And it's a great little formula that's going to help us compare the lattice energy between different ionic compounds. Now, the lattice energy has a very specific definition. It's the energy that is released, right? Because I'm forming an attractive force. So I take my gaseous, it's got to be cation in the gaseous phase, anion in the gaseous phase, and then forming the solid ionic compound. So it's the energy that is released when attractive forces are formed. So freeze to form attractive forces. Now, this is going to, in turn, once we can do that, help us compare that structure function link in what I call a next chapter in your next topic, the next segment that you would be looking at is how does the structure impact the function? I'm going to introduce that by comparing melting points. Now, I want to point out that when we're using this formula, we're assuming that these bonds are purely ionic in character. Well, ionic moves into polar covalent, moves into covalent behavior as really a continuum. So if it deviates from this, we start to say that, well, we must be seeing increasing covalent character to the bond. Okay? Now, what we will use for lattice energy is that it's a constant, and I'm only going to use it qualitatively, times the charge of the positive, charge of the negative over the distance. And we will be looking at that absolute value of that. So if it is negative, it's the energy that is free to form. If it's positive, it's the energy that it would take to break. Maybe I won't do that. Let's do it this way instead. So just bear with me on that. I think I don't like that. Let's really make it clear. If that lattice energy is negative value, we're talking about the energy that is freed to form. That value as a positive, if it was reported as a positive value, that would be the energy that it takes to break. So if we were back at this picture, energy going in the forward would be negative, but if I went in the reverse direction, that would take energy, that would be positive. Okay, so hopefully that gives you the general idea. One of the key things that you want to do here is define distance when you use Coulomb's law. And I'm not using R squared because that's the force of attraction. I'm looking at potential energy, which is distance. And it's the distance between the ion centers, so it will be the sum of the atomic radii. So the distance would be the radius of my cation plus the radius of my anion. Okay, now we had a lot of kids on the AP exam lose points because they didn't define their distance very clearly. Right, so we want to be really careful about that. Now, let's look at some examples of these. All right, so I have lattice energy reactions. So I'm going to we're going to form, I'm not going to be able to write small enough so that I'm going to do it down here. I'm going to form magnesium chloride solid. And I'm going to do that from the gaseous magnesium ion and 2 chloride ions, and it's got to be gaseous. You need to know that. This is one of the energy equations, much like ionization energy, that you need to know. And then the other one is sodium chloride, and we're going to take a look at those. So we have sodium ion gaseous plus chloride gas yields magnesium chloride. Excuse me, Dena. Oh, Dena. It's something my kiddos hear a lot. NaCl. And that's going to be a solid. Okay, so now what you always want to do is you want to compare charges and you want to compare radii. Radii of your cation, radii of your anion. Now, the radius and charge of our our anions is the same in this case. So I need to just look at the positive charge and the radius. And in this case, I always say charge trumps distance. I'm always going to predict it's the higher charge. So I would say magnesium chloride is our winner in this case. So let's take a look at the next one. We've got lithium fluoride and lithium chloride. Okay, so I've got lithium, let's again do it down here. Lithium ion gaseous plus fluoride ion gaseous going to solid lithium fluoride. I'm wondering if I say that enough, you'll memorize it. And then I have lithium ion gaseous plus chloride ion gaseous going to lithium chloride solid. Okay, so again, we want to compare their charges and their radii. Well, the positive charge and the radius of the cation are the same, so I don't have to worry about that. That won't influence my decision. Now, in this case, the negative charge is the same, so that's a tie. Now I need to look at the radius of the anion. And remember, as you increase the distance, you decrease the lattice energy. You make it lower or more negative. Okay? So, in other words, the closer they are together, the more attracted they are. The more attracted they are, the greater the energy it's going to take to break. So in this case, lithium fluoride is going to be the winner because this is the smaller anion. These two are closer. The closer you are, the greater the attraction. The greater the attraction, the more energy that it takes to break that attraction. Okay, now we have one more. And so I have sodium ion aqueous plus chloride ion aqueous. I'm getting tired of saying this, but I'm hoping if you say, oh, Dena, oh my gosh, what did I do? And I'm not even going to start over because this teaches us a lesson. It's gaseous, gaseous. Gaseous ions go to solids. Be careful. Look how easy that was for me to mess up. So strontium 2 plus and chloride is going to give me solid strontium chloride. Okay, so now as we evaluate this, the chlorides are the same. They're not going to influence it. So what we find is based on radius of the cation, the sodium ion wins. Based on charge of the cation, strontium wins. If I'm going to predict, this might not be always true, but based on prediction, this is double, whereas the radius doesn't typically double. I would predict strontium chloride would be the winner. based on its charge. So hopefully this helped you out. I'm so glad you joined me. Have a great day.